We're still now in the chapter of nucleophilic and electrophilic aromatic substitution. And just to kind of recap where we left off, because the thing that we're about to start talking about that's new is going to basically be based on this last bit of notes that we just wrote. Now, we were looking at groups attached to aromatic rings, and we were asking the question, like, depending on what's attached to the aromatic ring, is it going to be electron donating or is it going to be electron withdrawing? And so the first example that we looked at was inductive electron withdrawal, all right? And that was basically using your knowledge of electronegativity. So if there was an electronegative atom directly attached to the aromatic ring, whether it be the halogen or an oxygen or even the nitrogen by comparison to nitrogens, by comparison to carbon, these were the examples, right? So the halogens, alcohol groups, if you had a carbonyl directly attached to the aromatic ring, if you had a cyano group, if you had a nitro group, those all basically fit the bill. The next example was inductive electron donation. And again, by that was any sort of organic spinach that didn't have heteroatoms or electronegative atoms attached to it. So alkyl groups in general, methyl, alpha, isopropyl, these kinds of things. And the reason for that is by comparison to an alkyl group, the aromatic ring is the more electronegative group. So you can think of that pool of electron density for an alkyl group being able to set up partial negative charge in the ring, partial positive charge there. And then we discussed, let me see if I can get this to zoom out. Then we discussed other examples of resonance electron withdrawing. And all of this was really looking at resonance structures that you can generate whenever you have, and this was the example, pi bonds that are in conjugation to the aromatic ring. So going back to that chapter of conjugation, what you're looking for is that double bond, single bond, double bond motif. Now, if you have that double bond, single bond, double bond motif coming from within the ring, outside into the ring, and so that's why the groups that can do that will be carbonyls directly attached to the aromatic ring, cyano groups, nitro is a really strong one that can do that. And then the last one we said was resonance electron donating, all right? And for that one, that was, again, going back to what we know about resonance, looking at allylic positions. If the allylic position to any of the double bonds of the aromatic ring is a heteroatom directly attached to there that has a lone pair of non-bonding electrons, be they 1, 2, or 3, in the case of oxygen, nitrogen, and the halogens, then either of these groups here, the halogens, alcohols, ethers, and amines, would be examples of groups that would be strongly electron donating. All right. Now, I mentioned that this is a really important thing to commit to memory, because now what we're about to look at is how those groups activate and deactivate certain positions around the ring. So to my knowledge, I think you guys have a handout that I think is due next week that you're supposed to fill out. Now, for the most part, it looks pretty easy because we've gone over every single one of those reactions that are in that handout. But what we haven't done is we have not discussed the order that those things, the synthesis should do in order to place them exactly where you want to go. So what you should be able to do now, after having sat in my lecture, is if you go through that handout and if you look at the reactions where it's only a single thing on that aromatic ring, then you're now armed to be able to solve that. So I think there's like 2 or 3 problems in there, and then 2 of them are actually examples directly out of the lecture that you should be able to do. But any of the ones that has 2 different groups, or even 3 different groups on there, you're not going to be able to know how unless you've been reading ahead of the book, right? So today is where we start looking at activating and deactivating groups, and that's built on the knowledge of what groups are electron donating and what groups are electron withdrawing, right? So let's go ahead and talk about that. We'll title this activation, deactivation of aromatic rings. Right, so I'm not going to specify what the group is attached upstairs to this aromatic ring, but I'm using this as the model to remind you about the nomenclature that we should commit it to memory, because again, we're going to be referring to these positions the ortho, meta, para, with regards to whatever that group is upstairs, right? And so the first example of a substituent on an aromatic ring is going to be the alkyl group. And so the textbook example for that would be toluene, which is the principal component of paint thinner, which is simply methylbenzene. All right. Now what we're going to do is we're going to simulate, right, on paper, the nitration of this aromatic ring that has this methyl group already on it, right? And if you recognize that there are 3 different positions that that nitro group can attach to, right? The nitro group can either attach to itself in the ortho position relative to the methyl group, in the meta position relative to the methyl group, or in the para position, right? Which is either going to be 1, 2, 1, 3, or 4. And so let's draw all the possibilities for that substitution, right? This would be clearly the one in which you have the nitro group being at the ortho position. This would be the nitro group at the meta position. And then the final one would be the nitro group at the para position. Again, with regard to the methyl substituent that was there in the original starting point. All right? And so, what we can say about alkyl groups, we can say that they are ortho-para directing. We can say that because as a substituent, it is weakly donating, right? And we mentioned earlier in the previous page that alkyl groups can donate electron density inductively. And of the 2, I should say of the 4, the inductive electron donation and the inductive electron withdrawal, those are the weaker 2 of the 4. The ones that involve the resonance, the last 2 on the previous page of notes, those are the strong electron donating. Those are the strong electron withdrawing types. So the alkyl group is weakly donating. And what you find is that you can anticipate 65% yield at the ortho position, 34% yield at the para position, and about 3% at the meta position. Does that even add up to 100? Off one here. But the point is, ortho-para get the lion's share. Right? So that means that if you're trying to decide the order of chemical reactions, and you have to put 2 things on that group, if the second thing you need to put on is a nitro group, and you're specifically trying to target the relationship that is meta, then this is probably not the best way to do it. It's probably not best to put the methyl group first, because if you do the nitration, you're not going to get the meta substitution in high yield. You're going to get these 2, right? So in that knowledge, and as we go through these, you're going to have to decide the order of things based on this. And that's how, when you go back to that laboratory handout, you can decide the order of the substitutions. Okay. So earlier we made reference to the sigma complex. And anytime that you have electron donating into the ring, it triggers a stabilizing of that sigma complex. So if you remember, the sigma complex is the reaction intermediate for all of these electrophilic aromatic substitution reactions. And so electron donating will stabilize the sigma complex. And if you remember, on the sigma complex, where those positive charges were when we looked at the resonance structure. So let me just briefly show you, because I remember I said that we'd come back to this. pages to start out here. All right, so sigma complex here. We, on the first page of this chapter, drew this. This is the positively charged sigma complex. And so you can see that the resonance of this places positive charges at the ortho positions and the para positions in this intermediate. And so what it means is that whenever you have something that donates electron density into the ring, the positive charges at the ortho positions and the para positions get stabilized. And those ends up being the positions that the substitution, then the second substitution, will occur at, which is why we see an amplification of the ortho and the para positions and not the meta. Okay. The next groups that we can look at, and these are going to be just two examples, knowing that there are a few others, is that if you have your alcohol group or your amine group directly attached to the aromatic ring. Right? Now, if you remember, this is the situation where the lone pair of electrons on the heteroatoms directly attached to the ring are at the allylic position to the double bonds in the aromatic ring, which from OChem 1 means we can draw resonance structures. And so alcohol and amines, and of course the other groups that place heteroatoms directly attached to the aromatic ring, are ortho-para-directing as well. And the reason for that is because this is the case of the strongly donating via resonance. And so the textbook example to demonstrate these distributions and yields, of course, is phenol. And we're going to stick with the same reaction. We're going to subject it to sulfuric acid and nitric acid, so basically nitration reactions. All right. And so this ends up being 50, this ends up being 50, and you get 0% of the middle. All right. Now, in this case, because these are the strongly electron donating, when we draw the resonance structures put positive charges at the ortho and para positions, which overlap the positive cationic charges that we see in the sigma complex, in the intermediate for this transformation as well. So they strongly stabilize the sigma complex. They put the negative charge into the ring, strongly stabilizing the cationic sigma complex. All right. So of course, alcohol and the amine are, just some examples. But let me give you a few more so we can label strong activators, which are ortho-para-directing. The example that we have are phenol. An even stronger example would be if you deprotonate phenol. So if you take phenol alcohol and hit it with a base, you can pull off the proton to generate the phenoxide anion, so O-. You can also hit it with sodium. We'll see those reactions in the next chapter to generate O-. But this is even more strongly donating because now you don't have two lone pairs on the oxygen, you now have three that can donate it to the ring via resonance. The other example that we just drew a minute ago is the amine, right? There's a lone pair on that nitrogen. And of course, those amines can be secondary amines. So you have some R group attached to that nitrogen, you still have a lone pair there. Or they can be tertiary amines. All right, so your nitrogen can have 2 hydrogens, an alkyl group attachment, or 2 alkyl groups attachment. Now, if you were to put 4 groups on that nitrogen, then you convert it to an ammonium center, you make it cationic, and then it becomes much more charged and becomes electron efficient. So it only works for primary amines, and then of course the secondary and tertiary amines. Now I do want to point out that we've labeled this last group of molecules strong activators. And there's a very good reason for that, because now what I'm about to give you is a list of moderate activators. And the strong activators versus moderate activators, they're not really going to play a role so much in putting 2 things in an aromatic ring, but they're going to play a major role when you put 3 things in the aromatic ring. Because once we start putting that 3rd thing on, then you're going to find that 2 of the groups that are already on there will start being either ortho, meta, para directors, and sometimes those can overlap. And then it's a matter of, well, which one was the stronger director, and then that determines where the 3rd thing goes. So it gets a little bit more convoluted as we start to add more and more things to the aromatic ring. All right, so I'm just pointing out that this use of this verbiage, strong activators, we're gonna have to refer to that a little bit later. Does anybody still need this up? All right, so those were the strong activators. These next examples are moderate activators. Now, they're activators nonetheless, so these are still ortho-para-directing. Now, here's an example of a moderate activator. And it makes a lot of sense why something like this wouldn't be a strong activator. If you notice, all the strong activators had heteroatoms directly attached to the aromatic ring, and thus the only thing basically that can pull or push electron density with it was the aromatic ring. Here though, we find that we still have the heteroatom, so in this case this is an ester. We have the heteroatom oxygen directly attached to the aromatic ring, but alpha to that oxygen is a carbonyl, which we know can withdraw electron density. So that removes a little bit of the ability of that oxygen at the aromatic ring to be able to donate electron density into the ring. And so that's why something like this is a moderate activator, whereas something like phenol would be a strong activator. All right. So then, having sort of spilled the beans on why that is the case, then you can imagine the same is true for amides. So this would be an example where you've got the nitrogen as the heteroatom, but of course, unlike the ester, the amide is the carbonyl nitrogen alkyl bond. And then of course that nitrogen can be a tertiary amine in the amide itself, so that one would also work. And then in this case also ethers. Now, the one group that is what we would call the exception are going to be the halogens. Now, the halogens are the exception because they do withdraw electron density inductively because they're electronegative. But the halogens have 3 lone pairs of non-bonding electrons. And so those can donate into the ring. And so what you have competing is the fact that you have those 3 lone pairs of electrons that would be directly attached to an aromatic ring, right? This would be true for iodine, fluorine, chlorine, bromine. But it's electronegative, so they're competing against each other, and it turns out the one that wins is the ability to put electron density into the ring. And so halogens, despite being electronegative, are still ortho-para-directing. But they're weakly deactivating, which means they're more activators than they are deactivators. So yeah, they do remove electron density inductively, but the 3 lone pairs of electrons that can donate in, they win out in that competition, right? So you can expect the ortho-para products to be the higher yields. Now, I also want to point out, just so that you're not confused, I'm only showing you the examples for the nitration. These rules apply to all those nucleophilic aromatic substitutions reactions. Chlorination, bromination, all those reactions still work. Right? But rather than giving you every single iteration, I'm simply saying we're using the nitration as the example. But it works for all the reactions we covered. So yeah, it's ortho-para directing. And just to kind of annotate the notes, it's weak donating despite being electronegative. And then I'll put here that it's weakly deactivating. All right, so these first examples that we covered are going to be all activators. They're all either strongly donating or weakly donating. These next ones, which we're calling the deactivators, of course, the examples we just went over are ortho-para directors, so I think it's academic at this point that, of course, it makes sense this should be the metadirectors. And these examples of metadirectors are strongly electron withdrawing. And the example, functional, the textbook example would be the nitrate. The nitrate would be strongly electron withdrawing. And I'll give you an example in just a second. So, okay, if I bring this down right there. So meta directors, as you would suspect, puts the substitution, the second substitution of the meta position. Now, the reason that the nitro group is meta directing, you might look at the nitro group and think, well, isn't the nitrogen a heteroatom that has a lone pair of non-bonding electrons? And if you thought that, you'd be wrong, right? And that's probably because we don't draw out what the nitro group actually is enough for some of us to commit to memory what it actually is. This is the nitro group. It is a Zwitter ionic group, meaning that it has charge separation, where you've got a full charge of +1 on one atom, and its counter ion directly attached to it on the same molecule with a negative charge to neutralize it. So it's still a neutral compound. But because that's the nitro group, you can see very clearly there's no lone pairs of non-bonding electrons on that. And not only that, but in this instance, we have a pi bond that is conjugated to the aromatic ring. And that pi bond, of course, is the nitrogen-oxygen double bond in this case. And so, you know, going back to the exam that I give in OChem 1, you might remember that in that exam where we give you resonance, the nitro group is on there. Because the nitro group can do some crazy things, like electron density can move there, that pi bond can break and go here. And I'm not going to draw all the resonance structures that are possible, but you're going to get the picture. That this allows for that group to remove electron density right out of the ring. And you can draw something like this. And of course, that can go on, and you can continue to draw more and more resonance structures. And when you draw the resonance structures from this, then what you find out is you put positive charges at the ortho and para positions, and that's what it means that at the end of the day, it's only the meta positions that have enough electron density to do the nucleophilic substitution. So groups that can do this end up being meta directors. And so like we saw for the activators, there are strong deactivators and then there's moderate deactivators. Right, so strong deactivators. The first one is, of course, the nitro. The nitro group itself, very strong deactivator. The quaternary ammonium, as I made reference to earlier, as the keeps moving. You have 4 bonds to nitrogen. It becomes an ammonium center and thus has a formal charge of +1. And ammonium centers are very, very electron withdrawing. They're electron deficient, so they're pulling out electron density directly out of the ring. And in another example, which is going to be one that we really haven't seen since OChem 1 in the chapter of acids and bases, the example for that would be trifluoroacetic acid. And we were trying to show you that trifluoroacetic acid has a much lower pKa than acetic acid because trifluoroacetic acid has the carbon adjacent to the carbonyl that's got 3 fluorines on it, which are 3 of the most electronegative atoms. So if you have an aromatic ring that's got a carbon with 3 halogens attached to it, then you start to find that that electronegativity induction and withdrawal is amplified. So for something like this is just as electron deficient as that. So these are very, very strong electron withdrawing groups, and thus they are strong deactivators. And if you see them on the aromatic ring and you're trying to do a substitution on it, that's electrophilic aromatic substitution, then they're going to be meta-directing. You're going to be putting things in that meta position. Anybody still read this up? All right, so the next thing we're going to do is just go ahead and list out the moderate deactivators, that way you're aware of what they are. And I think you're going to see structurally similarities between them. These are also meta-directing. So these are going to be the groups that have the pi bond in conjugation to the aromatic ring. So here's an example. This is some unknown aromatic ketone, but that also means that aromatic aldehydes also work. Aromatic esters, provided that the carbonyl is directly bonded to the carbon that is in the aromatic ring. So esters, it also means that carboxylic acids. It also works with amides. Acids or sulfonate groups, and then cyanide groups. So all of these groups are meta-directing, although by comparison to the nitro groups, quaternary ammonium centers, they're moderate in their deactivation.